We'll go ahead and begin. Just quickly made this problem up from just off the top of our heads, and it's really not the best problem, and we'll explain what that means here in just a moment. Okay? If a lion is moving over a distance of 47 meters in 4.18 seconds, and is moving at 7.18 meters per second. I'm just kind of ad-libbing. I'm just jumping all over the place. So you want me to just go in order?
Yes.
Okay. A lion has a mass of 425 kilograms and is moving at 7.18 meters per second squared. What is the animal's momentum? Okay. If it begins from rest and moves 47 meters in 4.18 seconds. Okay? So, you read the problem. What is the next thing you should do?
I know what we have.
And do we need to keep saying that over and over? But you might be surprised. We get to an evaluation and people choose not to do what you just said. And why would someone choose to either not write this down or do these how we work together in class? They might be lazy or it's too easy. Is that too easy for anybody in here? And maybe it is. I mean, that is an answer. But moving forward, what do we know in this problem? Okay, I got, maybe you were saying variables in here, but I got none of that.
Well, I'm saying the line is have a mass of 400 kilograms.
Okay, so we have a mass of 425 kilograms. Okay? What else do we know?
Velocity of 7.8 meters per second.
Are we sure? Why are you right?
Our initial velocity is 1.8 meters squared.
Right. So when we look at this, remember this is a trap, okay? Movement can not only just be velocity, it can also be acceleration. So when you're looking at this, you have to pay attention to the label. We have an acceleration then of 7.18 meters per second squared. Because if it was a velocity, we wouldn't have that squared value on there. Okay? What else do we know in this problem?
We got 47 m.
Okay, which is what?
Meter.
Well, yeah, I know it's meters,
Or
but what variable is that?
VF.
No, it has something to do with that.
VI.
What did you say over there? Okay, Izzy, what is it?
Distance.
It's a distance. That's right. Is anybody upset yet? Look at what we have up there.
Mad.
We're mad. Yeah,
That's
probably.
pretty good.
Well, I thought so.
Ward
Mrs.
says-
Herbert, are you mad? I'm mad. I get mad from time to time.
Ward says damn.
Okay. Yep.
Both of them are.
So sometimes it's an old cliche. Cliche just means something that you use that as an expression that I don't like the frog. The frog needs to look before it leaps. I know that's a cliche there. There's other ones you could say. And one of them is mad as a hatter, since we got mad up here. What do you suppose it means if you're mad as a hatter?
As a what?
Mad as a hatter. Hatter.
Like a mad hatter? I've heard of it.
Are they? How did you know that? I didn't think anybody would come up with that. Because you're right.
What is it? She's just smart.
Did you just pluck that up off the apple tree or what?
No, I had to use the distance and the.
We're talking about two different things here now.
She got it out of
Yeah.
her backpack.
I didn't say anything about the Mad Hatter. That
Oh,
was her. I think crazy.
how did you know that?
Because Mad Hatter's crazy.
I know, but What makes him crazy though?
He has
Doing
so many
science? That could be.
hacks. He's got too many
I think it was back in England when clothing makers were, there was mercury involved in there somehow. So that mercury was absorbed by their skin, and eventually it makes them go crazy. So when we say mad as a hatter, it's because they've gone crazy. Not upset, but they've gone crazy. Okay, so what else do we know in this problem?
The final velocity is 4.818.
Maybe, but no, not quite. It has something to do with that.
It's time.
Okay, so we've got a time of 4.18 seconds. So we've ran out of numbers. What is the question asking for?
What's the momentum?
Okay, so what do we have to solve for any momentum? Okay, well, we've got our mass, but what about our velocity? Do we have a velocity?
No, we need a
No, that's why when you look at this, okay, we know that it's a product that we have to have, which is a mass and a velocity. But we only have half the equation. So we have to solve for one part of the problem, take that answer, and put it into the second part. That is why writing this content down is so important. Yes?
What does the P mean?
It's a product. It's just a variable. That's all it means. Do you have your formula sheet handy?
Yeah.
Well, that's your problem, but there should be a separate page where you wrote out your formulas.
Yeah, because Herbert made the formula for me also.
Okay.
It's in the
Well,
folder.
well, there's one of your formulas. There's a formula. And then it would be P equals M times V. Okay? So that's what the P means, just a product. Okay. Now this really isn't a very good problem, and we'll state why that is in just a moment. Yes?
I thought P equals, like, P stood for momentum, but we can't use M again because it's
Right.
for mass.
That's, I said, it's a, what did I say? I said product of mass times. Yeah,
Or-
yeah, it means product of a mass times the velocity. Okay? And do we really need that variable? No, we don't. Okay, for two reasons. One, we have an acceleration up here with enough material to solve for that of a final velocity. Or, what can we do?
It's over time,
Distance over time. Okay?
the final velocity.
So then, once we find our velocity with that, what would you do with that answer then?
It would turn into your final velocity.
It would, and then let's take things one at a time here. Your final velocity then, okay, or just velocity equals, what's on the right-hand side of that equation besides a line?
The 47 over 4.18.
Okay? 47 over 4.18. Okay? So then, how do we solve for that velocity then?
You divide them.
Okay? So rather, can we just have one person only?
Okay,
What do we get when we divide that out?
11.24.
Okay? So notice we're not going to be using that variable. Like I said, I didn't write this problem out very well, but now we've got enough information.
Mr. McKinney?
Yes.
Is that our final velocity?
It is. Yep. Because we could presume that they're starting from rest and then moving this distance in that time. So we can say that that's a final velocity. Okay? Again, this is just half of our problem because we have not solved for momentum yet. And how would you go about doing that?
Mass times final velocity.
Okay. And we got, what, 425 times 11.24, and what do we get as a product?
4,777. Nothing else.
Oh, okay. Comes out even? Wow, okay. You don't get a decimal? Oh, you don't? Okay.
Did you ask how you got that?
How did we get this?
Do you remember the
Okay,
formula?
do you remember that formula you just wrote? That formula you just wrote down a minute ago? Okay, what's on the right-hand side of that equal sign that you wrote down?
The velocity
And, that's right,
and the mass.
right. So what that means is we take that information and we put it into this equation. So what is your mass now?
425.
Okay. Okay. And then what is your velocity now?
11.24.
Okay. So, yes. So if we're taking our mass times our velocity, which we need to do, how do we illustrate that then? There's 3 different ways you could do it. You could put this, you could put a dot. What did we do yesterday maybe?
The parentheses.
Right, so we could do that too. So then, what I want you to do is with your calculator, go ahead and put that in your calculator.
Yeah, isn't it 4,777?
4777.
Right. Okay, so how do we label this now?
Meters per second.
Kilograms, not minus, per meter over second. Okay? So that's what we mean. Show your setup work so you can look at what the question's asking, because you can't solve for momentum right away because you just don't have enough information to do that. Yes? Yes. Okay? All right. Let's maybe, well, before we go any further, front row, are we on the bus? Okay. Second row, you're going to answer for your lab partner. Now, the reason I say that, whether it's that table or that table or that one, I'll say, since you two sit next to each other, you're the lab partner. So that's why I say you can answer for your lab partner. Okay? Back row, are we on the bus? Micah? Okay? Okay. Can we erase this then?
Yes.
All right. So I'm going to do one more problem quick. Then let's see here. Don't forget what is important about today and tomorrow. And what as I look over on the board, when is that vocabulary due? It is?
Tomorrow.
What does it say?
Vocabulary says
8 slash
29.
8 slash
28.
8 slash 28. That's today.
So what sheet is that?
The assignment from Monday.
Oh, the first assignment we got was for the notes. And the vocab you didn't do?
No, it's not. The vocab
Oh, that says worksheet 1 due 8/28. So that's today. Okay, maybe we said vocab. How many of you are done with your vocabulary? Probably a lot of you. Okay. So, yes, vocabulary tomorrow, worksheet today. I just glanced over at that. So, my mistake, your fault. Okay. Did you catch that?
one day.
No one caught that. And why are we throwing things? Or we're just doing this? I'm not seeing things. Right? Okay. But no one caught what I said. Now, Now we kind of lost the,
Context?
yeah, part of that, yes. I said, my mistake, your fault. I made the mistake, but it's your fault. Yeah.
No.
It doesn't work that way? All right.
Works the other way around.
Okay, you're probably right. So, one of the things, let's just do this illustration quickly. Got the side of a building here, and this is something that perhaps a forensic scientist would possibly look at in solving. That it's got a slope top here. It's supposed to be straight, but it's not. We'll make a straight top on here.
What is this?
Well, this building keeps on going. This is just a cross section of our building. So we have, now if you draw this, fine. If not, that's fine too. The drawing just might help you try to illustrate what's actually going on. So we have a person up here on top. Okay. I can't draw very well. He's thinking, he's got a black eye. He's only got one eye, it looks
His
like.
foot's hanging off. We gotta save him, Mr. McKinney.
Yeah, that could be. There we go. And maybe he's got a little hair. Okay. So you know it's not me. Okay? So one of the things that maybe this building is on fire. We all right back there?
He's gonna jump, I understand.
And he's going to jump. Okay? And so what happens, so here's the ground here. All right? Or maybe this is a crime scene where this person gets pushed off the side. Okay?
He jumps into a dumpster.
Because what happens here is that what type of component is this?
Gravity.
Yeah, it's a vertical component due to gravity. So now, after, we're going to say 3.5 seconds. We got 1, 2, 3,
0.5.
and then we got a half here. Okay? So 1 second, 2 seconds, 3 seconds, and then 0.5 seconds. Okay? So, what happens is on a building,
Mr. McKinney, are we supposed to write this down?
He's writing his email.
You don't have any questions.
did I not say you don't? Well, someone heard what we were saying. I don't know. Someone's listening over here.
Good
Okay?
job.
So how many total seconds do we have that has elapsed approximately? It's not going to be exactly 3.5, but because of this, the path that they travel, how many total seconds have gone by?
3.
3.5. 3.50. Hits the ground and they survive. Okay? Oops. Okay. Then oops. I'll make that a question mark then. I'm going to put a little hint here because we already answered this as this is a what type of component?
Gravity.
Well, It's a vertical component, so you must compensate for what?
Gravity.
Okay? So remember to account for gravity. And we presume, I don't like the word assume, so I always say presume. Okay, so we presume the because one of the things that this is going to be a reoccurring theme, we might say stand still. We might say from rest. That's an important aspect because when you say, wouldn't that be something if I didn't turn this on? When we say beginning from rest, why is something like that important? True, that's their starting point. What can you presume? Well, let's start with this. You've read the problem. What do we do next? For probably the 13th time that we've said this. Well, how many problems have we gone over? I bet it's at least 8. Okay,
8.
solve it then. So what would you do next?
Probably write the numbers down.
So then, why are you not doing that? Was it confusing what we said, maybe what to write down, what not to? What did we say maybe you don't have to write down? The building. Was that confusing when we said that? No? Okay, well, that's your choice. Okay? So when this happens, what do we know in this problem? What do we know? Okay, so the time, 3.50 seconds. What else do we know?
That gravity is.
Why is that important? Because it has a specific value.
Gravity?
It was illustrated in a previous problem. Maybe we did, Mrs. Herbert, you haven't been in here every time, but I thought, did we not assign gravity as a specific value? Oh, we did not. Okay. Objects will accelerate towards the earth at a constant rate of this. 9.8 meters per second squared, because we had said, I know we did this. You can presume that when it's free falling, that it's 9.8 meters per second squared, because it's in a vertical component. But in a horizontal one, it probably won't be 9.8. It can, but chances are it's going to be greater or less than that. Okay, so we know the acceleration then. And even if we didn't put a variable over here, how do we know that this is an acceleration?
Because that's how fast it's pulling down.
Well, true. See, I like the signs, because farmers do it all the time. Because I grew up on a farm. I'm used to using signs like this. You're saying this and you're pointing at that, right? Yeah, so squared. See, I can interpret that, all right? Great minds think alike, okay? So we have an acceleration of 9.8 meters per second squared, okay? What else do we know?
That you have.
There's one really key component. Just tell me. Why is that so crucial? Okay? So we're starting at 0, but what might that be? 0 what, though?
Initial velocity.
Which is measured in what?
VF.
Okay? So meters per second. So we know it's a velocity. So is this the first one or the final one? Remember, they haven't hit the ground yet after they survive this. So it's an initial velocity. Okay? So what is the question ultimately asking?
How high is the building?
So we really can't do anything with this, but this is our clue right there. Because what does the acceleration formula tell you?
Then it's not.
Well, that's true. So look at the information that we have, and what could you solve for by looking at that formula?
You could do 9.8 times 3.50.
Okay? You're visualizing that in your head. Why are you correct? Because you probably looked at your acceleration formula, so let's go ahead and do that. You have an equal sign here. Okay?
A equals
What is on the left-hand side of that?
9.8.
9.8. Okay? We've got a fraction over here. So what goes on top of that fraction?
3.5 over 0.
Mm,
No, it was 0
Other
over
way around. Okay? So we have to account for something up here, because you correctly said this is on the bottom. Well, what's on the top of this fraction? You could say 0 and
VF.
0 is VI. That's why we write it down. VF. Whoever said VF, that would be correct. Your final velocity then minus 0. Do we have to have that 0 in there? No. You can presume you're subtracting by 0 or adding 0. Nothing's changing. Okay? So how do we solve for this final velocity now? Because you said it back there, so now just put together what you had said. What was that?
Multiply 3.5 and 9.8.
I think you're stealing your lab partner's idea. Didn't you tell me to do that?
No, I did.
Oh, you did. Oh, well, it's in the general vicinity. You can take credit for that. Why didn't you say I said that? You didn't want to do that from your friend. Okay. So a good way of illustrating that is put a fraction over here. And what would that fraction be? 9.8 over
1.
1. Okay? We have not changed that 9.8.
Then you can do the 9.5.
You can. So what is 1 times VF? Just tell me.
VF.
VF. Okay? So that must equal by multiplying whatever that is.
34.3.
Okay? And that's labeled in what?
Meters per second.
Meters per second. Okay? So that's only part of our answer. Okay? Because what is the question ultimately asking?
How high is the building?
How high is that building? This is not going to give us a height. Okay? But once we have a velocity and you look at your formula sheet, what can a velocity do to help you with a height? Right, close. Because when you say that, if we have a velocity and a time, what can we solve for? Distance, which in this case can be height. Okay? Distance can be how high it is off the ground. Okay? So upon doing this, if we were to, I've been using black, I'll go back to this color again. What does, on the right-hand side of your velocity formula, what goes over there on the top of the fraction?
34.3.
Say that again. Distance, or D. Okay? What goes on the bottom of your fraction? Which is, again, we don't have to look up in the problem. We see that it's right here. So it's 3.5. And then what's on the left-hand side of our equation? Not 9.8. You got the right idea, you just picked the wrong one. Say that again.
34.3.
Why are you correct? Oh, because your lab partner told you. Well, see, that's where you look at your lab partner and say, thank you.
Thanks.
And then, okay, you can say, you're welcome. All right. But you had said acceleration. That doesn't work because in your velocity formula, just velocity, it can't be meters per second squared because that's an acceleration. We need to put a velocity here. And like you correctly said, 34.3. So how do we solve for that distance now?
350 divided by 34.3.
I don't know if we're dividing. Okay, now answer this question here. What is 1 times d? And then you cross multiply there, you're going to cross multiply here. So one person only. 120.25. What then?
0.05, not 2.5.
Oh, okay. Okay. And what's that labeled in? Meters. Okay. Is that rounding up to? It's is it 0.047 or something?
No, it's exactly that.
It's exactly that? Okay, that's what we're going to go with. Okay. Back row, are we on the bus? Front row. Middle. See how we continually mix this up a little bit. All right. Notice when we do these, and on the papers, we're going to put a circle or a box around your answer. That just really speeds things up for myself because you got to take into account there is 32 papers we're going to collect, okay? And there's 10 problems, right? So that means how many total problems are we going to read to correct? What's 32 times 10? 320. So that's a lot of answers to go through. So that just really helps me out. Then, once you get this paper handed back to you and it's got a score on it, I would hold on to that, not only because of until your exam is done, but also that you can confirm that it's in the grade book. Because it sometimes happens, I'm going to pick on yourself, you might turn it in and yours might be stuck behind hers. And then I skip past it inadvertently. It's graded, but it didn't get in the grade book, but I pass it back. That way you can say, I've got the score right here. Does that make sense? Okay. Any questions on that paper that you're about to hand in that you would like to address? Because if you have a question, chances are somebody else might. Yes.
Number 2.
Okay?
Like, there's a lot of things I don't like get how to do, and
Okay.
like formulas.
Okay. Number 2. Keep in mind, did anyone else have questions on number 2? The reason that's tricky, now let me help you out here, is because you're making a comparison. You're going to be doing that a lot this semester. You need to come up with an answer and compare it to information in the problem. Okay, so we're not going to write the entire problem up here, but doesn't it have something to do with an alligator? Crocodile. Okay? So what can you tell me about that crocodile with its variables? It has like a velocity, a time, distance.
It says the mighty crocodile can strike its prey with amazing speed and accuracy. As the animal swipes its
tail to thrust out of the water to grab a wildebeest at 1.65 meters above the water's surface. The croc can move at an astonishing 4.30 meters per second. If the crocodile moves out of the water in less than 0.10 seconds, then the wildebeest is its next meal.
Okay, so what that means is, what does it say in, just hold on, what does it say in parentheses? It says solve for what? It says solve for time. Because you're given time in there, but it's saying solve for time and make that comparison. Okay, now what's your question back there?
Did you write wild beast on purpose like that?
It should be wildebeest? Okay, well, I don't know. Yeah, you probably should say wildebeest instead of wild beast.
Can I use the Russian engine?
In a few minutes. All right. So, how do we solve for this time? Let's look at what formula are we going to use. What formula do we use?
E over T.
V over T?
Yeah.
Distance over time.
Okay, so distance over time. Do we know the distance?
Yeah, 1.69.
Okay, do we know the time?
No.
Do we know the velocity?
Yes. Which is 14.3.
Okay, I'm willing to bet that some people, I bet there could be one hand that goes up if they're being honest. How many people multiplied across? It's what?
14.309.
Oh, okay. All right. So, how do we solve for time?
You put a 1 under 14.3.
You can, okay? So, what is 1 times 1.65?
1.65.
What is a number times a letter?
The letter. 14.30 T.
Okay? So we need to get t by itself. So we divide each side by 14.3. And what do we get for a time? Say that again. Okay. Should this be 0.2? 12?
Yeah,
Yeah.
Okay.
because we round up.
If we round up, okay. Now, it said, even though this is striking with amazing speed, that wildebeest can react in 0.11 seconds or less. Okay? So that mean that if it took 0.12 seconds, was that in time or is that too late for that crocodile?
Late.
It's too late. That animal gets away. That's what we mean by comparisons. Okay. Any other? We have time for just one more question. We don't always do this, but this is the first one. Anything else you'd like to add that we can point people in the right direction, or is this it?
I didn't get to do 7 or 8. I was
Okay.
working on this with Mrs. Herbert.
Okay, well, continue to go ahead and do that. Okay, as long as you, if you're willing to help yourself, we're gonna throw you a bone, in other words, or you're throwing us a bone, saying we can see that you're trying, and that's what we like to see. All right, we'll catch up to you next time.